Alright, so unit 11 number 4 is the same, almost the same thing as unit 11 number 3. Same reaction occurring, it's just we have different amounts of HCl. I'll write them up here again. We have 25.2 milliliters of 0.2 molar HCl, and we have 30 milliliters of 0.15 molar, I'm just going dimethylamine. Okay, so same thing as before. You want to calculate the amount of moles of each you have so you can see if you're at the equivalence point, beyond the equivalence point, before the equivalence point. Last time we were before the equivalence point because we had more weak than strong. This time we have equal amounts, and so that means we are at the equivalence point. Exciting, yay. Okay, so our total volume, also important, 52.5 milliliters, just add those two up. So that's part A. Part B, it's still the exact same reaction as before. So we can just skip the explanation for that. Part C, still using the Brahe table because at this point we are still using this driven reaction. So you just fill it out. Before you have 4.5 millimoles, 4.5 millimoles. Cl minus doesn't matter, 0 millimoles. In this case, you don't have a limiting reactant. You have equal amounts of both, so they're both completely going to be used up. Minus 4.5, minus 4.5, plus 4.5. That means here you have 0, 0, and 4.5 after the reaction. So for part D, when it asks what is present after the reaction is finished, we have 4.5 millimoles of CH3 to NH2 plus. And we have water as well, which is important for this one, because this is, again, all in solution. And yeah, so normally we don't have to care about the water, but for this one we do, because there is going to be a reaction occurring after this reaction, because you do have this weak acid, and then that will react with your water to form an equilibrium. So here we'll set up our ice table, R for reaction. So we have our weak acid that we made up here, reacting with the water. This will make an equilibrium because this is weak. And since it's an acid, it will donate an H to the water, so we make H3O+, and then we make our dimethylamine again. So that is our reaction. Now the next thing we need for ice tables is everything has to be in terms of, well, okay, I'm just going to get rid of that right away. But everything needs to be in terms of molarity, whereas up here we needed it in terms of moles, we need it in molarity for here. So just like how we calculated molarity up here in question 3, you take the millimoles you have divided by the total milliliters, and then that will give you molarity. So we have 4.5 millimoles, and we have 52.5 milliliters, so that is 0.0857 molar of the weak acid. So 0.08, what was it, 57? Yeah. That's our starting molarity, and then 0, 0, and now this is just our typical ice table problem. So minus x plus x plus x, x, 0.0857 minus x. The Ka, right, we solved for that in question 3 as well, so I'm just going to go back up here. We know Kb of dimethylamine is this. This relationship we also know, so 1 divided by 10 to the negative 14th, or 1 times 10 to the negative 14th divided by 5.4 times 10 to the negative 4th gives us our Ka. So we're going to use that down here. So that was 1.852 times 10 to the negative 11th equals our expression here, so x squared divided by 0.0857 minus x. Again, we can assume that x is negligible or x is small, as you guys say here. And then we multiply through and we end up getting x equals 1.2598 times 10 to the negative 6th. So I didn't really do the math to see that it really is negligible, but this is times 10 to the negative 6 and this is 0.08, almost 0.09, so it's pretty reasonable to assume that this doesn't have a major effect down here. Yeah, I didn't actually do the math, but we're gonna go with it. And this x, as we can see here, now represents the concentration of H3O+. And so to get the pH, which was our end goal, we just take negative log of x. So negative log of this 1.2598 times 10 to the negative 6th. You end up getting pH of the system is 5.90.